Hello, am I audible?
Yes, sir.
Okay. Wait for 2 minutes and then we start.
Hello, sir.
Yeah.
Good evening, sir. Actually, graded 2 assignment solution is not available in the supplementary section. So, will it be available?
Uh, Graded 2 deadline is over, right?
Yeah, it was over, sir. It was last week, no? I mean, 12th.
Okay.
Also, graded 3 and 4 have the same date, sir. I mean, 19th. But is there a possibility to postpone graded 4, sir? Because we are still in graded, week 3 itself. It's taking
Mm,
time to understand. So, both
Unfortunately,
3.
no.
Okay.
The reason is the course started on 20th January, right? So 20th Jan it started, right? So 20th Jan was the release of week 1. So 27th Jan should have been deadline for week 1. Okay, so the deadline
Mhm.
for week 1 got extended by 2 weeks. So it got
Okay.
extended by 2 weeks initially, and then it's like very tight. Unfortunately, it is you won't be able to extend it, but try your
Okay, so
best.
because that's fine, sir. Because I mean, it's taking time to understand each and every concept because full of formulas and theories. So it's taking time to understand, work out, and do it. That's it. Thank you, sir. No
Yeah,
issues.
yeah. So give me some time and just move things around. So I won't record this meeting because I have started streaming. I hope that will work. Streaming link is everyone able to see the streaming link?
Yeah, it's visible.
Okay, I hope it will stay that way and we don't have to record it in any sense. Okay, so streaming is on. Let's start. We have a quorum, so it's good to start.
Sir, should we personally record the session or it will be uploaded in the portal?
No, it's already streaming. So I have added the link to the calendar. So I'll also add it to that Excel sheet which we are maintaining, right? So I will also add it there. You don't need to record. So I'll
Okay,
so
from the calendar we will get the YouTube link, no?
from the calendar you will get, but it's also better to refer to that Excel sheet, that Google sheet, right? Which we maintain in the supplementary content. We keep adding the links there. I hope you are aware of that sheet.
Yes, sir. Yes, sir. Yes.
Okay. Right. So what we'll do is, since it's back to back today and tomorrow, we have back to back sessions. So today we'll go over the concepts like briefly, and then tomorrow evening we'll discuss the questions. Since it's closer to the assignment deadline, the discussion of questions we will slightly postpone to tomorrow evening. Today, let it be more of concepts. Okay, so that's the plan. So estimation and MLE. So there are like three parts to what I'll be doing today. One is estimation in introduction and maximum likelihood estimate. That will be the first part. Second part will be Bayesian inference. That will be the second part. Third part will be on GMMs. What are Gaussian mixture models? And fourth part, we're supposed to discuss EM, but I don't know if we'll have time or not. So we'll maybe quickly go over it. If not, tomorrow we'll do it. Okay, so that's the plan. Is there anyone who has not watched week 4 at all in this crowd? Can just give me a hand raise if there's someone who has not watched anything in week 4 lectures. Okay, so everyone has watched. Okay, that's okay. I have not watched. Okay. All right. So anyway, we'll be going over the concept. So I hope it will kind of brush up whatever is needed for the things, right? So see, the story so far has been as follows, right? We have seen two unsupervised learning methods, or three, but more of two methods only, right? We have seen representation learning and clustering, and finally we close it with estimation. So first 4 weeks for quiz 1, you will have unsupervised learning only, right? You won't have any supervised learning, and you need to know these 4 techniques or these 3 techniques going forward, right? So first one was again PCA, kernel PCA, we saw that, and then we started doing clustering using the Lloyd's or k-means algorithm, and now we are at estimation, right? So that is where we are. So what is the general theme that we have been following for all these 3 weeks, right, or 4 weeks in unsupervised learning? What, according to the professor, has been the common theme? Any answers, anyone? Does anything come to your mind? What is it that we are trying to do in all these 4 weeks?
Model the data, sir.
Okay, we are trying to model the data. That is correct, but little more precise. How are we trying to model the data? So, any other answers? Okay, in modeling the data, what assumption? Okay, not assumption, but how are we trying to model the data?
Sir, by learning the previous history.
Learning the previous history, okay. Not, no, I won't say it's wrong, but okay, that is another answer. Any other answers? What is that one line that the prof keeps telling? Arun sir keeps telling one line, right, all through the 4 weeks.
Describing the data.
Training the data.
Describing.
Okay, describing, training, not quite. Describing is okay, but how are we describing it? So, is there some process we are
by coming up with various algorithms?
Okay, all right. So if you look at all these 3 weeks, right, or 4 weeks, what stands? So if I say that, if I use that variable k, if I say k and just leave it hanging there, what can you make out of it? How is this variable k related to all these 4 weeks of content?
Sir, number of cluster.
Okay, k is the number of clusters in Lloyd's algorithm. Okay, what about first 2 weeks? PCA, kernel PCA. What did k mean there?
It's the top principal components.
Okay, it meant the top k principal components. Okay.
Best fit line among the data.
Okay, that is correct. Okay. What does k mean in the context of estimation? What could k mean?
Number of mixtures.
Okay, that is one k, but it's in some sense the number of parameters, right? So,
Sir, eigenvector, sir.
Yeah, that is in week 1, right? So the number of principal components. Yeah,
so
I think
those are the most important things to be considered in the data, and the remaining thing we can ignore.
Agreed. Yeah, these are the most important things. So what are you doing to the data in the process?
Does it talk about the dependency of the, the dependent variables and the difference between the dependent variables and the independent variables, sir?
So in unsupervised learning, there's no target variable as such, right? So they're all kind of features are all in some sense you treat them as independent variables, right? There's no target y that we have plotted.
Outcomes are unknown.
So we are reducing the number of data points and the dimensions basically.
Okay, so I'll take that final answer. I won't say we are reducing the data points. I would say we are compressing it, right? So this
Yeah,
is
Dimensionality reduction.
yeah. So this is the theme, right? We are achieving comprehension, which is understanding the data, modeling the data via compression, right? So as you all rightly pointed out, in PCA we are using K principal components and compressing the data, right? We are throwing away the other principal components. Top K alone we retain, and we compute the projections and come to a lower dimensional representation. So we are compressing it in that way and thereby achieving understanding. In clustering, instead of having all n data points, we are only looking at K important centers or K means, okay, and we are, and perhaps which point belongs to which mean. We also ask that question, and we can easily compute that, right? Closest, whichever mean is the closest, that is the index. So we are reducing all information available into K means, or we are compressing all information into K means. So in estimation, what we do is we compress all the information available into K parameters. Okay, this K could be different. For Bernoulli, it is just one parameter. For a Gaussian, it is two parameters. For GMM, it is say 3 times K parameters. Okay, but that's the theme that you have to understand, or the basic idea that you have to remember in all 4 weeks of the course that you have seen so far. You are trying to compress whatever information is available. You have chosen different ways to compress it. Okay, so that's the basic idea. Okay, so let's now quickly go into estimation. So estimation is looking at this, it's asking this question, right? So where does the data come from, or how is it generated, right? So what is the process? If there's something that is generating the data, and we call this some process, the distribution or whatever, right? We call it some distribution that's generating this data, and this distribution is having some parameters, and our whole idea in week 4 is to find out ways to estimate these parameters from the data, right? So that's the whole aim. Okay, so now I have this question that I want you all to have a shot at. So how do you think this is different from the first 3 weeks, or the first, so it's either representation learning or clustering? How do you think this is different from any of these?
Here we use probabilistic.
Okay, that is one thing. We use some kind of probabilistic approach.
estimation.
What is some other difference? Any other difference?
Here we focus on generating data instead of working on it.
Okay, that is a good way of putting it. We are focusing on generating, or the process that generates the data, rather than that's like very close to what I had in mind.
And then, this is going to be a bridge between supervised and unsupervised learning.
Okay. So I partly accept that, because you'll be looking at something similar in week 5. Sorry, not in week 5, in other weeks. So this kind of a generative process will be used in supervised learning. So in that sense, you are right. But this is still, we are still in the unsupervised learning domain, right? So that is also there. Any other one last answer from anyone?
We are some sort of estimating here. That estimation part can be say like
Are we making inferences from the model that we have prepared,
yes.
sir?
Making inferences from the model. Okay, that is correct. So I'll take these answers, and in terms of time, right? If you want to link it, so there's no time concept here, but if I say the word time, if I throw in the word time, does anything click, or will you change your answer based on this prompt time?
Estimation means future values. Estimate.
We can predict the future based on the outcome what we are getting out of the model. I mean, future prediction, that kind of a thing, sir.
Okay. Okay. So yeah, somewhat related. So I'll just go out and tell you what I had in mind. So clustering and representation learning, right? Or typically, what they do is they start with what is that, and you try to explain patterns. Okay. So for example, if you take clustering, you are given some data, and you try to find where there are lumps of data that are closely connected, right? So these clumps we call clusters, and you start working with it. In the case of PCA, you are given the data, and you try to find the directions which are most important in terms of, say, variance or representation, sorry, reconstruction error, right? So you sort of, right, what you do is you start with whatever you're given and then you try to explain some patterns. It could be clusters or it could be directions. Whereas in the case of estimation, what you do is you in sort of, right, these are all vague statements. You sort of move back into the past. You ask the question, okay, what actually gave rise to my data? Okay, so how did my data come here in the first place? So you can think about this as moving back in time and actually digging into the process that gave rise to your data set. Okay, so this is one difference. Again, it's not the difference, but this is one way of looking at it, which can, you know, separate these three methods if you want to put it that way. Okay, so this is estimation. It's a very brief introduction. So let's now go into this generative process, as we call it. Okay, so again, there's a simplified representation. I'm going to think about it this way. Any data set, it need not be simple scalar, single feature data set. It could be any sort of complex data set as well. I think of it this way. So assume that you have a bag of marbles. Okay, you have a bag of marbles, and what you're doing is, if you want to get this data set D that you have with you, you can think of this as picking one marble at a time from the bag with replacement. Okay, with replacement, and finally you end up with n marbles. Okay, so this is what we call the generative process. If you look at the lectures, what Sir would have mentioned is, you can think of the generative process as tossing a coin if the outcomes are binary, right? If the outcomes are binary, then you can think of it as tossing coins. If the outcome is, say, more categorical in nature, having six values or seven possible values, you could think of it as rolling a dice, okay, with 6 faces or 7 faces. Okay, so these are all different ways of thinking about the generative process. Now, another question at this stage is this. So we keep talking about independent and identically distributed observations, right? Samples. So in which of these arrows will you place this identically distributed part? Is it this arrow or below this arrow or below this arrow?
The second one.
Okay. What about others?
Second one.
Okay. Others?
Independent or identical?
Identically distributed.
IID.
Both, right? I mean, there are both.
But each one is. I'm saying it could. 1 second, so let me just think about it. No, the second one is identical. First one is. Second one is definitely identical. I don't know where to put independent. I would have put it in the same place actually.
Okay. So the bag stands for identically distributed, right? You are picking from the same bag.
The same problem.
Yeah.
So that is identically distributed. Independence is because moment you pick up one marble, you are replacing it back, right? So moment you replace it back, it's as good as the same bag. So the second draw of my or the second marble that I draw is kind of independent of the first draw, right? Because I've replaced it. No, it's as good as the same experiment done all over again. Okay, so the independence is associated with picking with replacement. So you can think about it this way. Whereas this identically distributed, why is it associated with the bag of marbles? Why do you associate?
Because it's you always have the same number of marbles, right? So
Same
probability of picking up something is it's the same probability.
Yeah.
Basically, the distribution is the same.
Right. So it's the same bag. Okay. So you could think of the same bag, and no matter when you pick up from it, you're going to get the same distribution, right? So this is one way of understanding the whole IID process. Okay. So there are certain, yeah.
Say for example, if we are not replacing means we are putting it back in the bag, right? We are putting it back in the bag, right?
We are putting it back in the bag, yeah.
Say for example, if I'm not doing that, then of course it is not identically distributed, because then my probability in the bag will be disturbed, right?
Not really. So that's what I also thought. In fact, I also thought exactly as what you thought.
No, say for example, if there are 3 red marbles, 3 green, and 3 blue marbles, right? So total 9 marbles are there, and the probability of picking any one marble is same 1 by 9, right?
Right.
But say for example, if I picked any marble, let us say it is green itself, and I'm not replacing it. So now only 8 marbles are there. So now the probability will be 1 by 8 of picking any marble, right?
So you have to look at the marginal distribution. Okay. So when we say it's independent, we are saying that we have to compute P of xi. So I'll ask you to go home and do this experiment of this working out of this thing, right? Assume that you forget colors, right? Assume that you have n marbles to begin with. Okay, and let's say you pick without replacement. Okay, they are obviously not independent. Any two draws are not independent of each other, but it turns out that they are identically distributed.
Independent is clear. It's not independent because what you pick up second time depends on what has come out the first time, right?
Yeah.
But at the same time, the distribution parameter changes as we don't replace, right? The parameter. See, the distribution family of distribution may be the same. It still may be a binomial distribution, but the parameter will change. Is what I'm.
No. That's what I also thought. You just go home and try this out, or maybe what I'll do is, it's not clear now. I'll post a question in discourse, and you can all think about it. Okay, I'm also not 100% sure about this, but very recently I read this while preparing for the session. I too thought that if you pick without replacement, I thought that it is also not identically distributed, but it turns out that even if you pick without replacement, this identical distribution part doesn't get affected in a very specific sense. So
So just a last try on this topic, and then we can move ahead. As you rightly said that we need to think over it again. So can I give, so as a last statement, sir, what Vasu was trying to say, say for example, in case of tossing up coin, right? So in a very layman understanding, when we are saying identically distributed, right? So whenever I am tossing the coin, so it is following that Bernoulli distribution kind of thing, right?
Yeah.
Either I will get head or tail. But here, when my bag is filled with marbles, and there are 10 marbles, correct?
Right.
So of course my number is going down, but the what you are trying to say, the family of distribution, so it will still follow the same nature of distribution, right? So
okay.
Can we look from this perspective?
What we are saying is not just the same family, right? So we say it's identically distributed not just when it is the same family, but when it's the exact same distribution. So
yeah, that's what has been our understanding so far. When we are saying identically distributed, so tossing a coin will follow Alois Bernoulli distribution, right?
With the same parameter p, right? So that is important.
Yes,
so,
with the same parameter p, right?
Yeah. So the identical distribution part means that P of x1 is also equal to BR of P, and P of x2 is also equal to BR of P. Right? The P doesn't change from x1 and x1 to x2 or any other xi. Right? So
okay.
So
then that makes a sense that what he said that parameter will change. So if parameter is changing, then how come it is identically distribution? Just for understanding, okay, we'll try it again at home.
It is right, because we are not considering. See, you are not considering the marginal distribution. So when we say P of xi, okay, I'll just very quickly maybe go over this because we may not have time. When you are picking with replacement, right, and without replacement. If you have n coins or n marbles in your bag, the P of x1 is what? Assume you have uniform.
So 1 by n.
This is 1 by n, right? So
right
now, what is P of x2? You're not replacing, right? So
1 by n minus 1.
Is that 1 by n minus 1?
Because now number of marble has reduced by 1.
No, right? So this is what? This is. So you have to look at this this is the joint distribution over. You have to consider all possible values of x1, sum over it, and get p of x2, right? So this is the marginal distribution of x2. Okay, so what we have in mind earlier is what? P of x2 given x1 has occurred. 1 by n minus 1.
Correct, yes.
This one, right? So this you are right. This is 1 by n minus 1. That's perfect,
Yes.
right? Now this will be what? I can. So how do I rewrite this? I can rewrite this as P of x1 by the chain rule of probability. P of x1 into P of x2 given x1 has occurred. I sum this over all possible values of x1. So for each possible value of x1, this is 1 by n, and this is 1 by. So for one case, it will be 1 by n minus 1. For one case, it will be 0, right? So if you pick so for one case, it will be 0. So I urge you. So I'm also not very sure now. I'm kind of fumbling at this stage.
Okay, sir, we can catch up later also.
Yeah, we can catch, right? So please go over this. But this is also identically distributed, and you will see why. Okay, if will be a nice discussion over this course, so we can.
Sure, sure.
Okay, so that is the IID part. For now, let's forget about that part, right? So they are all IID distributed, and the way we formally talk about these things is that you have a distribution, and then you're sampling from this distribution in an IID sense, and you end up with a data set. Okay, so that's what we are doing.
I'm sorry to take you a little back.
Yeah.
In identically distributed, do we mean, so for example, that that variable is distributed, say, binomially with the same parameter p, or it's just that they're both binomially distributed?
No, they have to have the same, exact same distribution. So
Parameter also is the same.
Should also be the same.
Okay,
right? So P of
there was this activity question in 4.1, I think the last question, where they were supposed to be in that box 2 coins with different probabilities, and we could not be sure which of the 2 would be selected. So we were supposed to find out whether it's independent and identically distributed. So I think the answer was that it is identically distributed.
Correct. So in that identically distributed part, right? So you will notice that the parameter is the same. So
you can different probabilities, the coins.
So you can.
Yeah. But if you add up, there is a way to solve that. I mean, if you go ahead. Sorry, sir. Go ahead.
Yeah. So you can actually show that the 2 coins can be replaced by a single coin, and that coin's p-value, right? So that is the parameter that we are interested in. So you can actually show that they are identically distributed.
Right, and it will be 0.6.
Because we would assume that of the 2 coins, there would be 50% chance of picking one and 50% of the other. In that sense?
Not in that sense. So, for example, see, let's say there are 2 coins, right? There is a probability P of picking first coin, okay? I don't remember what exactly that question was.
Can I respond to that?
Yeah.
Can I respond to that?
Yeah, go on.
So, sorry, I don't know who asked the question.
Divya.
But, Divya. So let's assume you pick 20 coins. 20 whatever coins, right? 20 coins. Okay. Now let's say there is P1 and P2, 2 sets of coins, right? So you are likely to pick 10 P1 and 10 P2, correct? Because they're equally likely. Yes.
No, actually, the question was more on the sense that there were 2 coins and we would flip them, and the probability of, say, turning a head, say, was as it was in the subsequent question, 0.3 and I think 9.
Sorry, which question? I'm confused. Which
You know, there's
question
that
is this?
coin in the box where you press a button and the coin gets flipped, so it either turns up a head or it turns up a tail. So now instead of one coin, there are two coins, and you don't know which of the two coins you're going to pick, but one has the probability of turning a head, say with 0.3 probability, and the other with 0.9 probability. So how are they identically distributed? This is what I didn't understand.
This is from the AQs or this is from the session?
It's from activity
AQ.
It's from the AQ, but which are based on the lectures.
Yeah, AQ had formulated the question differently.
It's 4.18 the question.
Yeah. So I was trying to solve that for you. Your question is, how is it identically distributed? I had solved this in my head, but sorry, sir, you go ahead and explain. I'll just try to recall. I know I've solved the problem in terms of the answer, but I'm just trying to figure out how did I say they're independent?
I mean, I know that the subsequent question does ask you what would be, the joint, if these two coins were replaced with a single coin, what would be the P of that single coin? Yeah. So I just did a lucky guess and I got the answer, but I didn't really understand the whole identically distributed concept.
Yeah. So if you think about this, it this way, right? So assume that there is a probability, there is a generative process, right? So the generative process is as follows. So the generative process is, first you pick a coin, okay? Second, you toss the coin and observe the outcome.
Right.
So there is a certain probability P with which you pick the first coin. Okay, I think in the question it's 0.5, but assume it in a more general sense, assume it to be P. Okay.
Right.
So if you pick the first coin, then there's a probability alpha that it will fall heads.
Okay.
Okay. Assume that that's my assumption. The probability of picking the second coin is 1 minus P, right?
Right.
So assume that there is a beta probability for that coin landing heads.
Right.
Okay. Now you're asking this question. I don't know what happened in between, but finally I observe heads. So what is the probability that finally I observe heads? Okay. So what you do in this case is you go by the generative process. So first you pick a coin. There is a probability of P for picking the first coin. And then given that you pick the first coin, there is a probability alpha that it lands heads.
Right.
Okay. Now this is exclusive of you picking the second coin.
Yes.
With probability 1 minus P, and then given that conditionally you will observe heads with probability beta.
Right.
Okay, now what we are saying is this is the probability of observing heads when I perform this generative process.
Right.
Okay, now no matter how many times I do it, the probability of this being heads is same. Okay, so let's call this theta. Okay, so what we are saying is this is Bernoulli of theta, right? I mean, so not equal to sign, but the probability of getting a heads, this particular random variable is distributed as Bernoulli of theta. Do you agree?
Bernoulli of theta.
Theta is given by this quantity, right? P times alpha.
Okay. So either we would get a head with the probability theta, or we would get a tail with the probability 1 minus theta. Is that
right?
What I'm saying?
Yeah. This is what
so in a way it's Bernoulli distributed with probability theta, which is given by this whole function.
Exactly, right? So this is now identically distributed because it comes from the same Bernoulli distribution with the same parameter theta.
Yeah.
And therefore you can, so it's like solving the second problem kind of helps you solve both problems.
Yeah. This makes a lot of sense. Thank you.
Okay, yeah. So going back, we have IID, right? So we have seen IID so far. Now let's move on to maximum likelihood. Okay, so we have fixed the distribution and we have the data set, and now we have assumed that a particular distribution will be appropriate for the data set. Okay, so now some of you might have this question. I think one of you already asked it in discourse. Given a data set, how do I choose a good distribution? Okay, so all the methods are fine, but finally, if I'm given a data set, how do I know which distribution to choose? And parameter estimation then comes later. Okay. So this question will not be answered in this course. Okay. At least this is outside the scope of the course. And I'll also acknowledge that I don't have the answer to this question. Okay. So in case anyone is able to find out a good answer, please upload it on.
Sir,
Practically, there's a
I
solution,
slightly
sir.
missed for 1 minute, sir. After explaining that problem, what did you say? Because my network was broken, sir. I know it is not more than 1 minute. After solving that problem, what Divya was asking, after that, what did you say, sir? Sorry.
Solving that problem, we were just
What Vidya was asking that Bernoulli distribution. No, you wrote, you wrote something in previous slide, right? After this, what have you said, sir? After moving to next slide, yes.
That's all, right? That's all. After this, we move on
this
to.
is okay. Yeah. After moving to next slide.
That's all. So
okay.
I just explain why this is.
Yeah, that's fine, sir. I was there up to that point.
Nothing else, right? I don't think anything else happened.
Yeah, this diagram you were saying something, distribution, then sampling, and all.
Okay. So here I was telling you that I don't know this part of how to choose the distribution once you have the data set. So see, what week 4 discusses is, given a data set, you somehow choose a distribution, and then it shows you how to estimate the parameters of the distribution. Correct? What we don't tell you is, how do you choose the distribution in the first place? What is a good distribution? Okay, so for example, we saw binary variables, binary observations, zeros and ones. So we chose Bernoulli. So if you observe categorical outputs, right, like zeros, 0, 1, 2, 3, okay, you will choose a categorical distribution. And if you observe real numbers, you'll choose Gaussian distribution. And if you observe something that's multimodal or bimodal, you will choose a GMM. Okay, so this much we have told you in the course, but we have not told you what to do if you are given, let's say, a data set with 100 features. Okay, what works for it? What distribution should you choose? So these things, you'll have to do some research and you'll have to enlighten us. Okay, so that is
practically there is, theoretically I don't know, but practically there is. Python has a package. It's called distribution fit, disfit or something like that. It basically checks against 72 standard distributions and gives it ranks the best fit in terms of, if this was this distribution, what would be the gap? What is the gap versus expected?
Okay.
So, and then you choose depending on your understanding and knowledge. Like, for example, if it is to do with number of visits in a shopping mall, it has to be Poisson.
Okay.
Yeah. So you broadly have that knowledge, plus this gives some indication. Basically, it's nothing. It's brute force. It's just trying everything possible.
Okay. So I'm not very sure. See, that's why I wanted you all to do some more research, right? See, for example, this will maybe work for a single feature, right? What about, say, 100 features? So we will have to think about some multivariate distribution.
I was coming to that only, sir. For single feature, I think we also perform goodness of fit kind of thing, right?
Okay. So I am not very much aware of that, but yeah, I that's what I'm saying. So please go research and kindly come back on discourse and share your ideas.
Okay. So I think for 100 features we can use the dimensional reduction possibly for the fit.
Dimensionality reduction
to get an idea of the plot, or distribution.
Yeah. So that's also a good point.
And if we talk about dimensional, we can also even use the PCA to reduce it.
Right. That's a good point. We'll come to that, right? So we'll come to that. I'll for now, I think, as some of them have suggested in chat, maybe I'll move on with the summary. Okay. So, but anyway, thanks for that. Yeah. So we have chosen a distribution, and now we have to estimate the parameters of the distribution. And the way we do that, or one of the ways we do that, is using the idea of likelihood. Okay. So I've written down the likelihood for a general case here. Now, is the likelihood a function of theta, or is it a function of your data set? Is your likelihood a function of?
Likelihood is a function of the data or the distribution. Is that your question?
Yeah, no, that is the likelihood a function of the theta, or
it's parameter theta.
Both, na?
We take help of data set to predict the parameter.
Isn't it both?
Okay, one of the answers is both. What? Anyone else?
I said parameters, sir. We take the help of data to predict.
Okay. All right. So generally, right? So generally, likelihood is treated as a function of theta. Okay. So on the left-hand side, you have the likelihood. On the right-hand side, you have the probability, right? The joint density of seeing the data set. Once you assume that theta is some fixed value.
Okay, got it.
Okay. So likelihood is typically when you go on the left, it's the same quantity, but then when you call it a likelihood, you are treating it as a function of theta. Now, why does this make sense? Why should I treat it as a function of theta? What are you maximizing?
So theta is the
So
set
if
of parameters.
So essentially, given a value, given a theta, what is the likelihood of seeing this data, right? That's what we are trying to maximize, right?
Right.
For what value of theta is the chances of seeing this data in its entirety, not just one part of the data, but the entire data is maximum, right? So
right.
You're looking for that theta which will maximize the chances of this data appearing.
Right.
So hence it is a function of theta.
Right. Okay, so we are looking for the theta, right, and which will be the best possible choice for generating this data, right? So it is more appropriate to view it as a function of theta. And anyway, if you think about it, the data is fixed, right? You are given some data set and you can't ideally change it. Okay,
yeah,
so
that's a very good point.
Right, so we are looking at two things. Of course, this is the problem we are trying to solve, maximizing the likelihood. But what you get out of it is the maximum likelihood estimator. Okay, as we call it, theta hat is nothing but the maximum likelihood estimator, and that's why we have an argmax here, right? Which theta hat is going to maximize the likelihood of seeing your data. Okay, so that's the maximum likelihood principle. Now let's go and look at likelihood and log likelihood. Okay, so you have likelihood here. So what is the next step after this? How will you expand this thing?
Yeah, it's product of individual, right? Because they're IDDs, right? So it's like intersection. So it will be the product of the value.
Yeah, so this is because they're IID, we can just write it down as product of each of the observations. Okay, and then we just say pi I equal to 1 to n p of xi parameterized by theta, right? So that's the likelihood. Now, this is the log likelihood. You just take the log. Usually we use small l for the log likelihood and capital L for the likelihood. Okay, so now the important question is, why do we care about the log likelihoods? Why not just maximize the likelihood? Why bring in log and all that?
Because taking the derivative of product is difficult, so that's why we take. So for finding the parameter which maximizes the likelihood, we need to take the derivatives, no?
Okay, I accept that as one of the answers. That is agreed. Anyone else? Someone raised their hand or mix product into sum.
Simple explanation for simplification.
Log is a monotonic function, so that is one of the reasons.
Okay, monotonic. Okay, that is also correct. Makes product into sum. Okay, so I'll take that makes product into sum. But let's dig into that a bit more. Why should you turn product into sum? Okay, one is the convenience of differentiation. Is there any other reason?
The log makes the value little bit smaller.
Kindly slightly correct your statement. You're right. You're almost
log
there,
actually makes because see these are products. As a result, if it's a large data set, the value will become very, very small because they're product of probabilities.
Yeah.
Right? And then you'll have buffer overflow situations and all in computation. If you take log, it actually the number increases to something which is sensible and there won't be any rounding off errors.
Right. So it's what is called the underflow problem, right? So overflow happens when you have huge values. So you have an underflow problem. So your computer may as well, treat it as zeros. So you have 100 data points and you have probability being 0.1, let's say. It will be 10 power minus 100, right? So that is as good as 0. So this is one of the reasons. I accept all the other reasons that all of you have given. That's also that. So the solution is to use log as it converts products to sums, as one of you pointed out. Now, you are now trying to maximize the log likelihood. So how is that fine? How is that acceptable? You try to maximize likelihood, but then you end up maximizing log likelihood, which is a different function. So how is that allowed?
Because we care about the parameter theta, which maximizes the likelihood function. No? So and also log is a monotonic function. Because of these two reasons.
Okay, so let's focus on this monotonic part, right? So log is a monotonically increasing. In fact, it's strictly increasing. So why does it matter? So how does it help?
So if the let's say the function is f and log of f, if log of f gets maximized at some point, then f also will get maximized at that point.
Okay, how is that?
Because they are like, it's just a rebasing, right? The log just rebases it. It's very similar. What do I say? Very similar trajectory. Is that the right word? I don't know.
Okay. Yeah, that's right.
And yeah, so and convex will remain convex, concave will remain a concave function.
Okay, so I'll take that. So what happens is log is strictly increasing. So assume that x star maximizes f. Then actually, what does this mean? F of x star. What is the relationship?
Sorry, x star and
x, any x.
So x star is the saddle. It's the whatever not saddle point. The whatever the what is it called? Shit, man.
Optimal point.
Yeah, there's another term, right? So it could be either minima, maxima, or saddle.
Extrema.
Yeah,
extremum.
I mean this is the maximum, right? So x star maximizes if if attains its maximum at x star, right? So because log is increasing, what it does is it retains the order of the elements, right? The order doesn't get changed, and this order preserving property is very important. So look at this implication go both ways, right? If f of x is smaller than f of x star, that's what it means to say that f attains its maximum at x star. Then because log preserves the order, log of f of x is also going to be less than or equal to log of f of x star, and this works both ways, right? So because of this nice property that log has, we can
sir, what is meant by order here?
Basically the increasing order, right? So if x1 less than x2, f of x1 is also less than f of x2. So it preserves the ordering between any pair of elements.
Okay, because the point remains the same, like.
Yeah, which point?
Like x star maximizes f, so x star will maximize log f also. So
right, yeah. So the point at which the argmax is going to remain the same, but only the maximum is going to change, right? So this is one more point. Let's move on very quickly. So let's look at the Bernoulli random variable, and let's do MLE for that. I think this is already done in the lectures, but I'm just quickly going over it. Okay, so probability of xi being 1 is p, and probability of xi being 0 is 1 minus p. So in general, for if small xi, right, small xi is the value of the realization of the random variable, how can you write this p of xi? There is a nice way of writing this.
P power xi into 1 minus p power 1 minus xi.
Yes, right. So that is the way you write this. So does anyone have any confusion regarding this? Because this is used in many places. Did everyone get this, or someone have any questions on how this came about? Okay, good. Right. So now we go for the likelihood, and this is the likelihood. So from this stage, right? How do I simplify this? Is there a way to simplify this?
Taking the log part.
Before going to the log, so
we could write p raised to some over xi.
Right? Yeah.
Okay, that's right. So what will that lead you to?
That would sum over xi gives the number of heads.
Very good. So what is the 1 minus p part?
The number of tails.
Okay, right. So that is correct. So p power number of heads into 1 minus p power number of tails. I've just used it as n minus number of heads, right? So it's the same. Okay, now you take the log. So you have nh log p and n minus nh log 1 minus p. What's the next step that we'll do?
Taking derivative.
Take the derivative.
Okay, take the derivative and you get this. Set it to 0 and you end up with some more algebra and you'll end up with number of heads by total number of throws. Okay, so this is what is called the maximum likelihood estimate. Okay, so for the parameter p. Okay, so I'm not doing the Gaussian part, which also amounts to the same thing, right? The mu hat will be sigma xi by n, the mean of the data points. Very similar, so I'm not doing that. So let's move on to Bayesian estimation if it's fine with all of you. Okay, we'll spend more time on this because this is slightly more involved than previous one. Okay, so start with simple things like the Bayes theorem. Okay, so see, there is one way of understanding the Bayes theorem in terms of beliefs, right? So there's this typical way of looking at two schools of statistics, right? So there is the frequentist school and there's the Bayesian school. So in the Bayesian school, you tend to look at probabilities as beliefs, right? So this is my belief that something will happen, or this is my belief that the parameter will take this value, right? So you look at beliefs, and in our context, assume that you have a data set D and you have some parameter theta for some distribution. Okay, so this is the usual Bayes theorem, right? So can you tell me what each of these terms refer to? What are their names? What do you call them?
P of theta given D is the posterior.
Okay.
P of D given theta is the prior.
Is it the prior?
P of D given theta.
Okay. Is it, you call that the prior? Think about it.
The likelihood.
Okay, that is correct. Yeah, you are right. What about?
Sir,
prior is that belief, no sir. Prior is that belief.
Okay, prior is some belief. Okay, what is the belief called? What is the proper term for it? So I got posterior, I got likelihood. What are the other two which are remaining?
P of theta is prior.
Okay, that is correct. That's the prior. So what is the last one? P of B?
It's the evidence.
That's the evidence, right? So let me just quickly go over this part. There's a nice way of putting this, which I like. Okay, so assume that you are, it's like a typical detective case scenario, right? So you're trying to solve some problem in some crime scene, right? And you go in before witnessing the crime scene. Assume that you have, because of your knowledge of solving several crime cases, you have some prior belief or understanding of the problem, right? So you have actually not seen the scene at all, okay? But you have some idea because of your experience, and that is coded in this prior, right? It's your belief, it's your preconceived ideas or your pre-existing notions of what is going to happen. Okay, this has got nothing to do with the data that you'll be seeing or the evidence that you'll be seeing when you actually go and present yourself in the crime scene. Okay, so this is the prior. Now, the moment you go to the scene, you get some evidence, right? You get some data. Okay, this is actually not this evidence, but for now, just stick with the idea of data, right? You see raw data in front of you. Okay, so something has happened, and what happens then is you had some prior belief, right? You use that belief to see how likely is the data that is coming to you. Okay, so you have some prior knowledge, okay, and you're seeing if the data that is coming to you, how likely it is to have happened based on your current understanding. So that is the likelihood, how likely it is that this agrees with my current belief. Okay, and depending on what this likelihood is, that is going to modify your prior belief, and that will result in what is called the posterior. Okay, so once you see the crime scene and once you process all the data, you're going to, your total belief or understanding of the situation is going to change, right? And that updated or changed belief is the posterior. What you went in even before seeing the data is the prior. How your data can be explained by your current understanding, that is your likelihood. Okay, and the Bayes theorem gives you a way of relating this prior belief, the data that is coming in, to your updated belief, which is called the posterior. Okay, so this is one way of processing the Bayes theorem. In our case, the prior is over theta, which is the parameter of some distribution. Okay, that is the prior. And D is nothing but the data set that is given to us. The posterior is what happens to your understanding of the parameter after you observe the data. Okay, so this is the setting. Now I have few questions here. What is P of theta? What kind of an object, mathematical object is it?
It's the probability mass function of theta.
Okay, that is correct. It's a probability mass function, or if theta is continuous,
it's a probability density function in that
okay,
case.
it's a probability. That's correct. Okay, so that's a density function or some distribution, right? So yeah, what you are saying is right. I use the term distribution, but that's inaccurate. It's a density. You should call it PMF or PDF, right? So you're correct. Now, what about P of theta given D? What kind of an object is it?
It's a conditional PMF.
Okay, but that's also a PMF, right? PMF or PDF?
Yes.
Okay, so I've just used the term distribution loosely, but what you're saying is more accurate. So these are, it's very important to remember that both your prior and your posterior are distributions, right? They're all probability distributions or density functions, which means they should sum to 1, integrate to 1, they should be non-negative, all that, right? So it's not a single value, instead it's a distribution. Okay, that's very important to remember in the Bayesian inference setting. What about P of D given theta? What is it? Is this also a density? Is this also a distribution?
Which one? Which one are? Sorry, I got.
So we are discussing about the likelihood. So
yeah. So, acha, P theta is also distribution. Okay. No, P theta by D also is a distribution.
Correct. Yeah, the posterior and the prior are both distributions, right? So that is established. Now we are asking, what is the likelihood? Is it a distribution or is it a simple single number like 1, 2, 3, and 5?
It's also a distribution.
Okay. Anyone else? Any other answers?
Is likelihood not a parameter? It is always parameter, right?
So theta is the parameter. What is P of D given theta, right? What is the likelihood? So for example, in the Bernoulli thing, right, we saw it was P power.
But still we are going for theta only, right? So is it not a single value?
Okay. Is theta
is also P of theta will also be a distribution, right? It comes from the prior distribution, much of the value. So
P of theta is correct. P of theta is a distribution, but what is the likelihood?
Oh, okay. Sorry, why am I getting
data is fixed,
yeah.
Na? So in that case, it should be a number, right?
Right. Not really, but
No.
yeah. So this is like a good point to ponder. See, it's actually just a function. Okay, it's a function. It's not a single number. It's a function of theta. You recall in the last set of slides, what did we say? We said that the likelihood is treated as a function of theta, right?
Yes, yes, sir.
Right. So in MLE, what did we do? In MLE, it's actually very simple. We threw away the prior. So just throw away the prior evidence posterior. What remains is MLE. Right. Just, if you only retain P of D given theta, it's MLE and it's just a function of theta.
Okay. Yes, understood. Thank you, sir.
And more importantly, should this sum to 1 or not? Should this integrate to 1? P of D given theta. Okay, it seems, again, this is something you can go home and verify. It need not integrate to 1, right? It's just a function of theta. Okay, so this is just a function of theta. I'll slightly, you can take some examples and verify. We'll come to that, but it's important to know that two of these that we are discussing, prior and posterior, are probability distributions. The likelihood is a function of theta. Finally, that leaves us with the evidence, the denominator. What is that going to be? Is that going to be a function of the data set? Is that going to be a single number?
Number.
Okay, that's going to be a simple scalar value, right? It's just a single number. Okay. So the evidence usually in Bayesian inference is a normalizing constant, right? So this denominator, usually you can get rid of it and move on. Okay, so that's another point. Any question about the Bayes theorem as such? Does anyone have any question?
Sir, not such a question, but this classification is a bit hazy still, because when we are saying p theta means on the right hand side, which is prior, and probability of theta given d, which is posterior, we are calling it as a distribution, PMF and PDF, right?
Right.
So in fact, PMF and PDF are also functions. So that's what we say, the probability density function or probability mass function, right? And then likelihood also we are saying function. Then how these two are different, sir?
Okay,
this
so
part is slightly not clear here.
Okay, so just a qualification, right? Density functions are also functions, but they are stronger in some sense, right? You have this condition that they should be non-negative and they should integrate to 1, right? You have those two extra conditions, which is what distributions have, right? And which any function doesn't have.
And similarly, when for the evidence part, the denominator part, when we are saying, so evidence is nothing but I collected one sample, right? And based on that one sample, I am saying some probability. That's evidence, correct?
Evidence is you collect some data.
Yes.
That part is correct. Now it is. So what you're doing is you're integrating over, or you're summing over all possible theta values that can explain this data set.
So the denominator part is nothing but a frequentist approach. Can we say like that?
I'm not sure if you can say it that way. But what we are doing is you have some data, right? Now, the numerator part, if you sum the numerator part over all values of theta, all possible values of theta, you get the denominator. Do you agree?
I agree. Just let us take one example. Say, for example, I am taking height of students in a class, right? So I picked a sample of 10 students, correct?
Okay.
My belief is that the average height is, say, for example, 160 centimeter, right?
Okay.
That is my belief and that is my prior. And then I picked a sample, correct?
Okay. Just one clarification there, right? So see, your belief is not a single value. Your belief is itself a distribution. You're saying that, so you observe heights of 10 people, and when you say that your average, on an average, I assume that the height is going to be, say, 160.
Correct.
That's a single value, right? That's not a distribution. So that you can't call that the prior in the Bayesian sense.
Now this is a little bit deviation, because till now this kind of concept was explained when we studied Bayes theorem in earlier courses. Then belief means, say for example, COVID has spread, right? So we are saying that okay, the spread is 0.8. Say for example, I'm saying, and then we are collecting data and then we are updating our belief. I may be wrong. It may happen that I had misunderstood that at that point of time in stats 2. But
no, your understanding is correct. That understanding is correct. What I'm saying is that, see, here the prior is not just a single value, right? It's not the, okay, so you can no longer just look at it as probability of an event. Okay, so that understanding is valid. But you are here, it's slightly more complex than that. Okay, so you're looking at a distribution rather than a,
because when we say Bayesian statistics, so it is nothing but it is completely based on Bayes theorem only, right? This is an extension of Bayes theorem only, not an extension. This is completely based on Bayes theorem. Am I right, sir?
correct.
Bayesian statistics is nothing but Bayes theorem only. The
Correct.
further extrapolation of that. Okay,
Yeah.
anyhow, sir, leave that p theta part. Explain this PD part, the evidence part, sir.
Come to that. We'll come to that, right? So there are some examples, and there are, when we look at the Bernoulli, it will become clear, right? Bernoulli.
Okay. Thank you.
Okay, so in the context of the Bernoulli, I think you would have seen the beta distribution. So let's very quickly look at those aspects of the beta distribution that are required for understanding week 4, right? So we have beta of alpha comma beta, and alpha and beta should be greater than 0. Now, can someone tell me what is the support of the beta distribution? Where does it?
0 to 1.
Okay, 0 to 1 is the support, right? So it will be, so the parameter of interest P of the Bernoulli distribution, we are trying to model that using the beta distribution, and P lies between 0 to 1. Okay, so this is a good choice of distribution here, right? And now, can someone tell me the form of the distribution? How does it look? The PDF?
Not like normal.
Sorry?
Normal distributions.
No, right? So
left tail or right tail? Right skewed or left skewed?
okay, but if you look at f of p, right? If I were to ask you what is the density of the beta distribution, f of p, just like you have the normal distribution's density as e power whatever, right? Okay, so this part have you all gone through in the lectures?
Yes, sir.
Are we talking about p to power alpha minus
P to the power of alpha
minus p
1 minus
beta minus 1?
Yeah, exactly. That's that one, right? So that's the one. So this is the density, right? So please recall that these things are important from stats 2, whatever you learned. This is just, this entire week is in fact just rebranding of stats 2, some weeks of stats 2. Okay, so please refer to some of them if, in case you are a bit shaky there. Okay, so this is the beta distribution. Now, why do you think this beta distribution got the name beta? Is it because of this beta here? Is that the reason?
Alpha also is there, sir.
Okay, good point. So I could have as well called it alpha distribution, right? So it's not because of this beta. Okay, so it turns out that this normalizing factor, right, the denominator that you have here, which makes this function a probability distribution, which makes it integrate to 1, this is actually called the beta function. Okay, so this beta of alpha comma beta, this is actually capital beta in Greek. Okay, so that's why it got this name beta distribution. And this is the actual value. Okay, this is not important. We won't ask any questions based on this. But in case you are interested in, so in the lectures you would have seen this as capital Z. Okay, so this capital Z is actually beta of alpha comma beta. Okay, so we'll quickly go through some of the shapes of this beta distribution. I want you to focus on the shapes because that will help you understand the rest of the session. Okay, so what can you infer from these two shapes? Alpha equal to 2, beta equal to 5. Here alpha and beta are flipped. So what kind of inferences can you draw from this?
For beta 2,5, it peaks at lower value of the random variable.
Okay, that's good. For beta 2,5, smaller the value of p, higher the value of the density, right? So Is there a way you can link that to the form, the functional form here? Why do you think this happens?
It depends on alpha and beta.
Correct. It depends on alpha and beta. In what sense? So what is the relationship between alpha and beta here, and how does it influence this whole thing?
When alpha is small, the first peak, right?
Okay, so when alpha is small, it peaks to the left of 0.5. Can we say that?
Then beta.
Yeah.
Okay, why is that the case? Can you infer that by looking at these symbols here? When alpha is small, why should it peak to the left of 0.5?
Because when P is more, it will towards, or I can say when beta is high, it goes towards. No, that won't work. Sorry.
Because the probability of the favorable outcome, whatever it is, that P, its power gets reduced as alpha is smaller than beta, and the probability of that not happening increases.
Okay. Okay, so when P is small, what can you say about 1 minus P?
1 minus P is large.
Large, yeah.
Okay, so when beta is higher than alpha and when you're closer to 0, what effect will this term have? 1 minus P power beta minus 1. Okay, so let's take concrete values. Let's say P is 0.1, right? 0.1 is quite small, right? So when P is 0.1, 1 minus P is 0.9. So I have a 0.1 power alpha minus 1 and I have a 0.9 power beta minus 1, correct? So when beta is higher than alpha, do you now see why smaller the value of P, higher the value of the function? Is it too, is it like going over the head a bit?
You're saying smaller the value of P, the higher the value of 1 minus P, and hence the higher the value of the function, given that the beta is high, right?
Exactly, yeah, that's what I'm saying. Okay, is that part clear to everyone?
Yeah.
Okay, so you can now flip the whole thing.
Beta value is greater than 1 or less than 1?
Sorry, which one? Can you repeat that?
Beta value is greater than 0 to 1.
Beta, currently we are looking at alpha beta greater than 1, right? So let's stick to that domain. So if you now swap these two, alpha and beta, you can now see, right? When P is near 1 in the second graph, when P is closer to 1, and if alpha is like say higher than beta, then you'll have something like 0.9 power 5 minus 1, which is going to overpower the other term, right? So when this is one way of understanding the shape of the beta distribution for these values of alpha and beta. Okay, so one quick way to remember is if alpha is small, the peak will be to the left of 0.5. If alpha is bigger than beta, then the peak will be to the right of 0.5. Okay, finally, that's the takeaway message, right? So if you can focus on that, that's enough. Okay, what happens if alpha is equal to beta? What do you think the plot will look like?
We'll have a symmetric curve. No?
Yeah, center, the peak might
Correct.
be.
Correct, right? That's correct. So it'll look like this. So no matter what, I mean not no matter what, as long as alpha and beta are greater than 1, it will look like this. Now let's take 2 more cases, 3 more cases in fact. This is when alpha is less than 1. The second one, this one is where beta is less than 1. Okay, just take 1 minute to understand this. See, if alpha is small, what did I say? If alpha is small, the peak will be to the left of 0.5. The same thing. If alpha is small, the peak, in this case, the peak is going to infinity, right? So the peak is the left of 0.5. If alpha is bigger than beta and if beta happens to be less than 1, your peak, instead of being some finite value, will go to infinity. Does this make sense?
Yes, sir.
Yes, sir.
There is one more way to understand this fractional values of alpha and beta. If alpha is a fraction, let's take the alpha.
This is a pure mathematical interpretation, right? So
this is pure math, yeah. Nothing, no practical consequences as of now. Okay, but we'll see the practical bearing of this in next 3 slides. Okay, now if alpha is, let's say, 0.5, why do you think this runs away to infinity here? Can you look at this and tell me why that happens?
Because p goes into the denominator, and lower the value of denominator, it would just go to infinity, no? Like,
very good. Okay, so please remember that when alpha or beta is a fraction, p ends up in the denominator, or 1 minus p ends up in the denominator. So depending on which of them is a fraction, the corresponding end of the graph will run away to infinity. Now what happens if both are fractions? How will the graph look like?
U-shaped.
Yeah, that's good, right? It look like a U-shaped curve because both are going to run off to infinity at either ends. Okay, so these 6 plots that you see here more or less summarize the different shapes that beta distribution can take. Okay, does anyone have any questions at this stage? Okay, so now one more.
Is there a, sorry sir, just a curiosity based question. Is there a phenomena which beta distribution kind of captures well in the nature, like shopping visits? We said it's Poisson, or interval between 2 events is an exponential distribution. Like, are there some natural events which beta distribution explains well?
I am actually not sure, but from whatever I read from Wikipedia, apparently they claim that beta distribution is good whenever you are involved with percentages, right? Because they're fractional values. They mean
okay.
So any percentage that you want to model using a distribution, you bring in beta distribution is what it claims, but I don't have any practical experience. So
okay.
Right.
So the last graph, the graph will not touch the axis. Why?
It will be asymptotic to the y-axis. In this part, right?
So beta 0.5, 0.5.
Yeah, it won't touch. It looks as though it is touching, but you are right. It won't actually touch.
No, the x-axis. It will not touch the x-axis.
X-axis, no, right? Because they are. It's all positive, no? All these things are. It will never be 0.
Okay.
Right. Okay, so moving on, we have 2 items related to beta which are important from both from the perspective of the quiz and even otherwise. So what are these red lines? And this beta 2,5, by the way. Okay, so what are these red and blue lines? What do you think they, green lines? What do you think they correspond to?
Mean and
median.
Median.
Mean is correct, but not really the median, I believe. What is the other?
Mode.
Okay, mode. Okay, mean and mode. I'll take that. Which one is the mean and which one is the mode?
Red
line is the mode, I think.
Why is the red line the mode?
Because it's at the maximum value of the function.
No. This is a distribution. This is density.
Right. So the mode of the density is the value where the density peaks, right? So you're right. I mean, for a discrete random variable, the most frequently occurring value is the mode, right? Now for a density, for a continuous random variable, the mode will be the value where the density peaks. Okay, so the mean for the alpha, for the, what is it called, beta distribution is alpha by alpha plus beta. Again, very useful formula for the course. If at all you remember anything, you have to remember this. Okay, you can forget everything else. The mode is Okay, don't be frightened by just looking at this. Actually, it's very easy to understand once you have understood the previous 6 graphs. Okay. So we'll derive this first part. So forget about the first part. We'll quickly go back and see what happens to the mode in these 3 cases. So if either alpha or beta is less than 1, you agree that the mode is going to be 0 or 1?
Yes, sir.
Okay, if alpha is less than 1 and beta is greater than 1, this is going to be the mode. On the other hand, if alpha is greater than 1 and beta is less than 1, this is going to be the mode. Now, if alpha and beta are both less than 1, what is the mode? You have 2 modes, correct? 0 and 1. Both of them are modes.
Sorry for a silly question, sir. Here, what is the mode means? I'm not getting it.
Okay, so the mode is in a discrete sense. You know the mode, right?
Yeah, the like -1 will be +1 or like that, and
No.
Sorry, I didn't get you.
Like the length value you are saying, or what?
No, in a discrete for a okay. So let's say you have you consider marks of students, right, in an exam. Now, if you have say 1,000 marks available with you, what will be the mode? The mode will be the marks which has occurred the most number of times, right? Right. So let's say someone, let's say 50 students have scored 90 marks, and nothing comes close to that value of 50 as far as frequency is concerned. So 90 is the most frequently occurring value, and hence the mode, right?
The most frequent occurring value.
Yeah,
right?
that value which occurs the most number of times is the mode. Is that right?
Okay.
Okay, in a continuous sense, what happens is actually not the probability, but it's the density. But still, somewhere around this peak value, right? If you think about it, somewhere around the peak value is what the mode is going to be. Correct? So assume that this, let's take this case, 0.5. So 0.5 is where the density peaks. And if you sample from this distribution, you will see 0.5 occur the most number of times, roughly speaking, right? Of course, they are real numbers and you won't exactly see 0.5 at all. Okay, so there's the probability of seeing 0.5 is 0. But in terms of density, if you look at it, somewhere around 0.5 is when I can see the most number of values come out of my density. Is that clear?
Yes, clear.
Okay, so now we are going back. So when alpha and beta are both less than 1, mode is 0 or 1. When alpha is less than 1, beta is less than 1, you see the modes what they are. What about alpha and beta when both of them are equal to 1? What do you think the mode is going to be?
0.5.
Think about it. When alpha equal to beta equal to 1, what is the distribution actually?
Alpha equal to beta equal to 1.
Is it some special distribution that you already?
Normal, sir.
Yeah, sorry, I didn't get.
It's like normal, no? It looks like normal.
1 minus 1 0 and 1 minus 1 0.
Okay, what does
alpha
that mean?
beta 1?
It's a flat line, no?
Okay, what is a flat line called?
Uniform distribution.
Constant.
Uniform distribution.
Yeah, it's uniform, right? What was was saying. So it's a uniform distribution. So for a uniform distribution, what is the mode?
All values of p from 0 to 1.
Right? Everything is a mode because all are equally likely to occur. Okay, now let's look at this. It will make more sense. So when alpha is less than 1, it is one end, which is the mode. When beta is less than 1, it's the other end. When alpha and beta are equal to 1, the entire line is the mode. When alpha and beta are less than 1, both endpoints are the modes. Okay, so I hope you understand these 4 subcases.
Sir, can you explain the mode again?
Okay,
what is mode?
What do you think from the discussion so far? What do you think the mode is?
The peak.
Is the peak, right? Or is it this particular value? Let's say 2.4. Is that the mode?
Inclination of peak, left or right or middle?
No, see, it is the point at which the graph peaks. Okay, so let's say it's 0.25 or 0.2 here, right? So 0.2 is the mode. 0.2 is where the graph reaches its maximum, and that is what we call the mode. Okay, can I move on? Is it clear?
Maybe my question will sound a little silly, but what is represented on the y-axis?
So you are plotting the value of p against f of p. So or rather f of p against p. You are plotting this particular curve or function.
Okay, and because PDF can be more than one, so it exceeds also one.
Right. Yeah. Only the area should be one, right? So the actual value can be more than one. Okay. It should only be non-negative, right? It should be non-negative, but it can go beyond one. In fact, it has to go beyond one if it has to given the shape, right? So at some point it has to go beyond one.
So we can say like this, right? The peak shows that 0.2 occurs many times, kind of like that. The probability of 0.2, right?
Correct. Kind of, right? Yeah.
Yeah, the probability of 0.2 occurs many times. That's what the graph says. I also don't know about the y-axis, but that's what mode means, right?
That's what mode means. So to put it slightly more concretely, let's say you draw 100 samples from this distribution. They're all going to lie between 0 and 1.
Yeah.
What the mode is telling you is most of them will lie around 0.2.
Yeah, 0.2 occurs a lot of times.
Yeah, that's right. Okay, any other questions before we go on to this final point regarding the mode? Okay, so to get this first value, right, the peak of this curve, when alpha and beta are greater than 1, you just differentiate this f of p with respect to p. Again, log is
Sir,
easier.
one more question.
Yeah.
Sir, sorry, sir. Alpha beta equal to 1, mode 0, 1. Alpha beta less than 1, again mode 0, comma 1. Same.
No, right? So this is an interval. 0, comma 1 is an interval. This is an interval and this is a set. Right? So if you notice, if alpha and beta are less than 1, you have only two values that could be modes, 0 and 1. Okay, so that is what this says. Whereas this is saying the entire line is the mode, line segment. Okay, I hope you got it. So now we look at this log of f of p. Now if I differentiate it and set it to 0, you can do this exercise. You'll get p to be alpha minus 1 by alpha plus beta minus 2. Okay, so it's like simple computation. You can try it out. Now this is the value that you see here. Basic calculus. Okay. Okay, now I'm moving on. Now we'll go back to Bayesian modeling. Okay, so you will see where this gets used. Okay, so the whole point of Bayesian inference is what? You start with a prior, some prior belief, and that gets modified via the likelihood into the posterior. Okay, so these are the three terms that are most important for us. Okay, so assume that you are observing zeros and ones. Okay, assume that you're observing zeros and ones. Therefore, the correct choice of distribution is Bernoulli. Okay, and the Bernoulli distribution has a parameter p. Now, what we are saying is that I have some prior belief about the values that p is going to take. Okay, and I'm going to encode this belief in the form of a distribution called the beta distribution. And the beta distribution has its own set of parameters. Because I don't want to use the word parameter again, this is the only parameter I have. I call them hyperparameters. Okay, so far, is there any confusion in what I said?
Can you repeat? I'm not getting it, please.
Okay, so See, you will see this term hyperparameters come across all the weeks from now on. So, for example, k-means, right? We studied k-means. No? In k-means, the value of k is a hyperparameter. Okay, because you are choosing it.
User defined.
Right? You are choosing k to be 4 or 5 or whatever. The parameters there would be in some sense the means, right? That you learn. Finally, you learn k means, but the k is not given by the k means algorithm. You choose k.
Yeah.
Likewise, here the parameter is p. Okay, p is not going to be chosen by you. P is something that the algorithm is going to learn for you.
Yeah, the distribution gives that parameter.
Right? Yeah. So alpha and beta are things that you are going to fix. So you are going to fix alpha and beta, and because of that you call them hyperparameters. Okay, so this is the setting. Any other questions?
But generally, in case of beta distribution, alpha and beta are treated as parameters only. Since we are using here parameter p, so just to avoid the confusion, we are calling it a hyperparameter. That's the understanding. Is it correct?
Correct. That is correct.
But in a normal course of time, we call it as a parameters only, right? Beta is having.
Yeah, out of context, in general, you will call it just parameters. But here, since you are already fixing p as the parameter, you will call them hyperparameters. But you will see this term occur throughout the course, right? From now on, at least. If you have not seen this before, you will see this starting from
algorithm and all, right?
Yeah, in all the classification algorithms, you'll have some hyperparameters to tune, and so it's good to be aware of such a term. Okay, so this is the prior.
Sir, one question can I ask you?
Yeah.
Sir, you are saying that xi follows the Bernoulli distribution because xi takes the two values 0 and 1. Yeah.
Right.
But why we are taking here beta for p? Any reason?
Yeah, there's a reason. We'll come to this, right? One very obvious reason is that beta has support 0, 1, right? So p is going to be a number between 0 and 1, right? So the least I should check for is come up with a distribution which can model p in the first place, right? So it should also have support 0 and 1, but there's a stronger reason which has to do with this conjugate distributions, conjugate prior. We'll come to that in like 5-10 minutes. Okay, so that's a stronger reason. Okay, so this is the prior. So I want you all to understand that this is a distribution or a density. Okay, so it's not a single number. Prior is a function that integrates to 1 and is non-negative. Okay, so that's very important. So what do you think is going to be the likelihood? Form of the likelihood. We have NH heads and NT tails. What will it be?
P raised to NH times 1 minus P raised to NP.
NT, right? So that is correct. So this is the likelihood. Now, how does your posterior depend on your prior and likelihood? You have understood whatever we have.
Multiplication, product of these two terms.
Okay, right? It's posterior is proportional to prior times likelihood. Now, why am I saying proportional? Why can't I just say equal to?
Because that PD part is missing here, denominator part.
Correct. Right? So posterior, remember, is also a distribution. It has to sum to 1 or integrate to 1. So unless I normalize it by the evidence, you cannot say it's equal to, right? It's not yet a distribution. So it is prior into likelihood. Now let's just substitute these two values. So P power, what have I done? Okay, I multiplied them, right? So do you see this, what we have done here?
One small question here, sir.
Yeah.
Sir, prior is a probability, right? The probability of like P being occurred.
So prior is a distribution of. So it's a distribution, right? It's the probability, yeah, in some sense, but it's a PDF. to be precise.
Okay, it's a PDF.
Yeah, what it encodes is not just a single number, right? So what it's encoding is something more than a number. Okay, I'll show an example. It will become more clear. Okay,
Okay,
just
please
hold
show
on.
the
It will
example.
become clear. So does anyone have any issues with this step? How we got the exponent like this?
No, sir, it's clear.
Okay, so we have just added the exponents, and this is proportional to beta of nh plus alpha plus nt plus beta, comma nt plus beta. Any questions here?
This NHNT you're using instead of xi and 1 minus xi, right?
Correct. Yeah, I mean I'm using them instead of sigma xi and sigma 1 minus xi. Okay, so sigma xi is nothing but number of heads, and sigma 1 minus xi is number of tails. Okay, now posterior now becomes beta of nh plus alpha, comma nt plus beta. Okay, so now the reason why we chose beta as the prior distribution is because the prior and the posterior end up having the same functional form. Okay, so we call this we use this term, right? Beta distribution is a conjugate prior for the Bernoulli distribution. Now, did everyone understand this phrase?
Yes, sir.
Okay, so this is important because of the following reason, right? So if you look at the evidence, which is what we forgot or not forget, but which is what we didn't divide by, is this complex integral that you have to compute. That's the denominator, okay? So if you choose some random prior distribution, you may not be able to compute this integral in the first place. So to avoid the difficulty, what you do is if you choose a distribution that is conjugate to the Bernoulli, then you don't need to worry about this part at all. You can completely circumvent the difficulty and instead directly update just these parameters here. Okay, any questions so far?
I didn't understand what is conjugate here imply.
Okay, so see, there's this idea of conjugate distributions, right? If two distributions have some kind of the same functional form, then you call them conjugate distributions. So in this case, the posterior and prior are conjugate distributions because they are both beta.
Right.
Okay, now you call a distribution a conjugate prior for some other distribution if it results in this posterior, which is also the same form as the prior. Okay, so what you have to focus on is that is this part, right? The prior and posterior should have the same functional form.
Okay.
Okay, you want prior to be, if prior is beta, your posterior, rather if prior is beta, posterior is also going to be beta under the Bernoulli distribution, right? Because you should always remember that this also matters. What you are multiplying with the prior also matters. So for this Bernoulli distribution, beta is a conjugate prior, meaning if you multiply likelihood with a beta prior, you will end up getting a beta posterior.
Okay. Will we be doing also the gamma and exponential?
Unfortunately not. We will be only doing this, but maybe we can spend some time, not today, but on the Gaussian distribution, which has a nice form. The Gaussian itself has the conjugate prior. So, and it has a good interpretation. Maybe we'll do that, but not
Sorry,
today.
the Gaussian has a?
It is itself a conjugate prior. So,
okay,
right. So if you think about it, it's all e power, right? So the summation happens over the exponents.
Yeah.
Right. So the functional form is retained, but maybe not today.
Yeah.
Okay. So there is also this idea of pseudo observations. I'll come back to this in the example, right? So I hope this example will make a lot of things clear if they are not already. Okay. So this is the hunch that Sarah is talking about in the lectures, right? So assume that you have not seen the data, The data is zeros and ones, but you have not seen it. But you somehow know that the coin that you're tossing is biased in such a way that the parameter p is closer to 0 than it is to 1. Okay, now can someone tell me what will be the prior distribution that you choose? Obviously going to be beta of something. What are alpha and beta going to be?
Beta would be greater than alpha and both will be greater than 1.
Okay, so can you give me some numbers? Small
Alpha
number.
is 2 and beta is 5.
Alpha is 2 and beta is 5. Okay, that's like very close. In fact, exactly what I had in mind. So alpha is 2, beta is 5, right? So this is why we were seeing all those shapes. Okay, it's precisely for this reason. So recall that if alpha is less than beta, then the peak is to the left of 0.5. Okay, so does everyone get why this is a good choice for the prior?
Yes, sir.
Okay, so p is closer to 0 than it is to 1. Therefore, I encode this knowledge that I have in terms of this prior. Okay, now I observe this data set. Okay, now prior is done. Now I need to compute the likelihood and then the posterior. Okay, so now what do you think will be the posterior?
Four comma 12.
4,2.
12.
Okay, that's one answer. Any other answers?
I'm sorry, I didn't get the question.
So did you get the prior, what the prior is and how this is done? Okay, so this is an appropriate prior. You have
Yes.
chosen the prior and then someone comes and gives you the data set. This is the data set that they give you. So now you have the opportunity to update your belief about the parameter p. Right? So this updated belief is what we call the posterior. So what is going to be the posterior?
Okay.
It's important. I mean, this is like the core of Bayesian modeling, right? This is something you have to be able to do.
Is it beta of 4 comma 12?
Is it beta of 4 comma 12? Yes, right. I think that's correct. So let's see what it is actually. Yes, that's correct, right? It's beta of 4 comma 12. So can you explain how you got it?
Because we know prior, we just proportional to that. So just what you explained, I just substituted. So.
Okay, right. So let's just go back. Notice that if your prior is beta of alpha comma beta, and if you observe NH heads and NT tails, then your posterior is nothing but NH plus alpha, NT plus beta, right? It's the same beta distribution, but with the number of heads and tails added in the correct places. Okay, so can someone now read this posterior and tell me practically what it means? What has happened here?
It just amplified, like scaled, right?
Okay, that's one observation. That is mathematical observation. So can you convert it into practical terms? In terms of the coin, what does it say about our belief of the coin?
It is almost the same, closer to our the
Our
original
belief
one.
has gotten stronger.
Yeah,
exactly, right. So that's the inference, right? So you had some belief. You said it was closer to 0 than it is to 1, and that was your prior, right? Now your data confirms it.
Yeah.
Right? Your data is now confirming it, so your belief has become even more stronger. To see why it has become stronger, you can see that it has grown in height, right? So you are even more confident that p is closer to 0 than 1, or your belief has been confirmed. Okay, so this is really the crux of Bayesian modeling, right? How do I start with the prior information and use my data to update my belief?
These beliefs are formed on the basis of experience or say some sort of expertise.
Correct. Yeah. prior to observing the data. So that part alone you have to hold on to. Your prior is formed before you view the data. But that as you said, that prior is obtained from your experience, expertise, domain knowledge, all that.
Sir?
Yeah.
Just a small clarification. Say, for example, if someone is following the frequentist approach, right? Not the Bayesian approach, correct? So in this case, the probability will be 2 by 9. It is as simple as that, right?
Yeah. So if you do MLE, it will be 2 by, I mean, if you just do the MLE, right, your estimate will be 2 by 9.
Yeah. If I do MLE, then so that's the frequentist approach, right?
Okay. I'm not sure. I'm not sure about that. Can we call it frequentist approach? I would say that what you said is correct about the 2 by 9 part, right? If you do MLE and estimate the parameter, then it is 2 by 9. But is it called the frequentist approach? I'm like not sure.
Okay.
Okay. So the belief in this case, the belief gets strengthened, and still please note this point because it's important. What you end up with is a distribution over P. You are still having a distribution over P. You still don't have a single number or what we call a point estimate. Okay. So that's example one. Now let's take, okay, before we complete. So I had this small thing right here. Alpha and beta are pseudo observations. What do we mean by that? It means the following, right? So you can think of your alpha and beta as some kind of data, pseudo data that you have with you even before observing D. Does this make sense?
Yes, because alpha corresponds to the heads, number of heads.
Correct. You are right. So the alpha corresponds to heads in some sense, beta corresponds to tails. So you can think of this as 2 ghost heads and 5 ghost tails, right? Or actually they didn't occur, but the idea is that you think of them as though they have already occurred, and now you are only adding your additional information in the form of D to whatever already exists in your head. You can think of this as what is there in your head and D as what you see in front of you. Okay, so in that sense, alpha and beta are pseudo observations. Okay, now we go to example 2. It's the same setting, P is closer to 0 than it is to 1. Now we observe a different data set. Now what is the posterior here? Okay, so I'm getting one answer in the chat. Beta of 9,7. Okay, is what I'm saying. That's correct, right? So beta of 9,7. I hope you all get it by now. We just add the alpha part to 2 and sorry, the number of heads to 2 and number of tails to beta. So can someone interpret this graph?
Yeah, it's our belief is not correct, right?
Correct, right? Our prior belief is not agreeing with the data.
Yeah.
Okay, so prior is not agreeing with the data, and therefore what you end up with is
completely shifted.
Yeah, right. So you're kind of confused now. In fact, if your prior had been swapped this way, right? P is closer to 1 than 0, then you would have obtained something like this, right? Your prior would have been something like this, and then things would have worked out. But here what happens is your posterior is kind of in the middle, right? It's in the middle, and it's roughly saying that it's about 0.5, 0.6. Okay, which is actually not true. If you do MLE, what you'll get is how many ones are there?
7 are there.
7, right? So 7 by 9 will be your MLE, and if you get a point estimate from here, it will be closer to say 0.6. Okay, so in this case, what we have seen is that if your initial belief is wrong or doesn't agree with your data, then Bayesian modeling may not P of much health. Okay. So one final example, P is extremely close to either 0 or 1. What kind of a beta prior will you come up with?
So can I ask one question regarding the previous one?
Yeah.
Might be I missed something here. Why we are taking prior as a beta of 2, 5 only? Any reason we are taking number alpha as a 2 and beta is 5?
The only reason is that I want to stay close to 0, right? So smaller values of P should have a higher density.
Yeah, so we can take any one, like 1, 4 or 1, 6.
Correct. Yeah, that's correct. So that's why the alpha and beta are called hyperparameters. They are under your control, and you can choose them whichever way you want. For example, you could have chosen a stronger prior, right? So say beta of 1, 10 possibly.
That is also correct.
That is also correct, right? So it depends on, say, if I change this statement to P is very, very close to 0 than it is to 1.
So we can take 1, 10 like this way.
Yeah, 1, 10, or maybe even so one of these curves, right? So that was the curve long way back, right? So if I say P is very, very close to 0, then I can even take beta of 0.5, 3.
Okay. So
right?
that's our assumption only, that we can take either 2, 5 or anything.
Right.
That close to 0.
Exactly. So for this, what will be the beta distribution? What will be the curves?
That less than 1 and equal, right? Which we had the graph, right?
Correct, less than 1. So let's.
Both are equal, yeah.
Okay, right. So let's take a specific value. It should look like this, right? P is extremely close to either 0 or 1. Will look something like this. And as you said, they should be fractions, and they should be, let's say, they can be equal, right? So beta of 0.1, 0.1. Now you observe this data set. What is the posterior going to be, and can you tell me how the graph will look like?
Yes, sir. The beta distribution would be 8.1, 0.1. And
What, 0.1?
8.1, 0.1.
Okay, that is correct.
1.1, sorry. 8.1, 1.1. Sorry for that.
Yeah, 8.1, 1.1. I hope all of you are also getting that. How will the graph look like?
The P point would be like near to
Alpha
0.
is higher. I think it will be near 0, right?
Yeah, near 0. Yes. Right.
Near 1, right?
Someone is
near 1.
So if alpha is greater than beta, then which side will the
it would be near 1.
Right side. Alpha
Okay.
is bigger than beta.
Okay, so yeah, that's a mathematical way of looking at it, which is correct. In terms of pure logic, right? How do you explain this? You had a hunch that it is close to 0 or 1, but you didn't know whether it was 0 or it was 1, and your data set had all ones but for 1, 0. So that is going to your evidence, or sorry, your data is going to now guide your original intuition towards 1. Okay, so it's going to make one side of your hunch stronger. So I think this is a mistake I made. It should be 8 point. I don't know why I made this mistake. It should be 8.1. Okay, so this is what you end up with. Okay, so is everyone clear about these 3 examples?
Yeah.
Okay, so here also it's another instance of your belief being confirmed by the data, and that updated belief being reflected in your posterior.
So one doubt in that example. So if the data is the other way around, if we get closer to 0, then also we conclude that it is correct. Is that so? Because now we have 2 options. P's.
So you mean if the data had all zeros and 1, 1? So then your graph will be tilting, shifted here, right?
Yeah, but according to your belief, that is also correct, right?
That is also correct. Yeah. So
we can get 2 kind of data, right?
Yeah, we can get 2 kinds of data, right? Yeah. The whole point of this example is to show that you may be very certain that your coin is biased, heavily biased. but you don't know the side of the bias, whether it's biased towards heads or tails, you don't know. And how can we use the data and Bayesian modeling to update your belief or to find out which side the bias actually is?
So here we've just confirmed our belief, right?
We have confirmed our belief. We have strengthened our belief. In fact, it's more than strengthening. It has given us one more information, right? So one aspect of our belief has been strengthened. So we already knew to start off with that it is heavily biased. It is just that we didn't know which side of it was actually the bias.
Right.
Okay, so that got confirmed here.
Sir?
Yeah.
But in an overall perspective, my belief, okay, I'm validating my belief and I am updating my belief based on sample, right? So it may happen that if I'm getting different samples, then it may keep fluctuating depending on the samples.
Yeah, right. Correct.
If my quality of input is not good or quality of data is not good, so it may keep fluctuating, right? So in that case, I won't be able to finalize, correct?
Right. So we are more looking at, given that we have some data set, how can we estimate the parameters in the best possible way? But if, as you're saying, if the data itself is noisy, then my parameter estimates are also going to be noisy.
So in that case, our sample size should be large, right?
Right. So if you are going to work with noisy data, yeah, you are right. So if you have a considerably large sample, then maybe the noise can be
minimized.
Yeah, the effect of the noise can be minimized, but yeah, so these are more empirical questions you're asking, for which generally I shy away from because I can't give convincing answers.
But so in practical life, we come across this kind of situation only, sir.
Yeah, that's true. Yeah. So see, the purpose of this course, right, is to introduce you to the techniques part of it and leave it at that, right? So if we stray away from that, what happens is I become uncomfortable because I know only till MLT. Beyond that, I am like.
Those are first statement. I don't agree that you become uncomfortable because we need an instructor like you and Srikanth, sir. Now you can proceed, sir.
Right. Okay. Yeah. So going on. So let's look at the final point, right? So after doing all this, you end up with the distribution over theta. Okay, the posterior distribution. It's still not a single value. So how do you get hold of this single value, which is called the point estimate? Okay. So I just written down the posterior on the right so that you have a reference to it. So there are two methods. There are actually many other methods, but we'll just stick to two. One is the mean, okay, which is just alpha by alpha plus beta, but this is like alpha plus nh, right? So first term by first term plus second term. That's how you have to think about it. The other one is the mode. Okay, so for mode, assume that the first term and second term are greater than 1, so it's the value that we saw earlier. Okay, so alpha minus 1 by alpha plus beta minus 2. Okay, so this is the mode. Now there is a term in the literature for the mode of the posterior. It's called maximum a posteriori estimate. Okay, so it's called the MAP estimate. It's very commonly used. It's nothing but the mode of the posterior. Okay, so it's a complex term for something simple. So if you see something like this in the exam, you must not get confused. What is the MAP estimate? If we ask, you must take the mode of the posterior distribution and enter that as the answer. Okay, is that clear? Okay, so that ends Bayesian modeling. That's all we have in these two topics. So any questions?
If you could go back to the answer we had gotten. So here, what would we say the mode is 1?
Here the mode is 1. Yeah, it will be very close to 1, and well, not exactly 1. You can use this formula, right? Both these are greater than 1, so you can use this formula. Alpha plus, so alpha plus nh will be 8.1 and beta plus nh will be 1.1. You just plug it in and you get the mode. It will be close to 1.
So this is the formula we must use in the exam.
Well, I would suggest that you remember this whole thing if possible.
Yeah, but I mean, if you want to calculate, okay.
See, it's actually very easy to calculate on the spot. I mean, you can differentiate this. To remember this expression, you just differentiate it and you can actually get hold of.
Okay. In an exam, it's easy if you have a formula.
Right, yeah. So
you can uploading this PPT, right?
Yeah, I'll be uploading it. Okay, so I have something on GMMs, but I think it's more appropriate if we do it tomorrow.
So just the last slide. Can you show once, please?
Yeah.
Just the one before this. No, just the last one. So this.
Sorry, 1 second. Let me just go to that.
This one, NH is number of positives, right?
Yeah, number of ones or hits.
Yeah, the wins or whatever we're looking for.
Yeah. Number of positives. Yeah.
Okay, thank you.
Okay, so I think the formulas should be correct. Just let me verify. This mode alone is kind of formula, and that formula are like tricky. So this alpha minus 1. Just remember this as first term minus 1 by sum of two terms minus 2, and the mean is just first term by first term plus last term. Here in the mode, you just subtract 1 from the numerator and 2 from the denominator. I hope we are doing that here. Subtract 1 from the numerator and subtract 2 from the denominator. Yeah, I think that's what we're doing. Okay, so we'll end it here. And any questions?
Yeah, once Karthik, it's a very fundamental doubt. I look, it's silly. See, data is given to us and we're going to model it, right? But in the middle, you yourself and even professors say often to generate data. That point I'm getting lost. Are we generating data? We're not generating data, right?
Good point. It's a very good point. So this gives you an opportunity to generate data. So moment you have estimated the parameters, right? So let me go back to the slide which had generative process, right?
So, but do we do that in the real world? Are we generating data? We are only analyzing the data, right?
Correct. I think, suppose there are two cases. What you said is absolutely right. Sir, Karthik, sir, please correct me if I'm wrong. So you're right. Its data is already there. When I think the word generative is being used to signify that what distribution can generate this kind of data.
Okay,
I think that's
what I'm getting lost often when they say both.
So what kind of distribution can generate this data?
Okay, that's okay.
And also if you want to create some synthetic data for some modeling purposes, you can use this process to generate that data.
From this we can also even get our own data for further testing or things like that, right?
Yeah. So in fact, it's interestingly, I actually wanted to do it this time, but I didn't get time. So I wanted to do a short introduction to language models. So if you look at this whole chat GPT, right? So you have the GPT stands for generative pre-trained. Okay, so there's GPT is by nature a generative model. So what we are doing in week 4 is actually setting the base for understanding generative models, right? So the synthetic data that we are talking about, right? So it's a very good example of how your GPT works. So you give it a prompt, it's a generative model, and it is what it's doing at the end of the day is it's generating tokens or words, right? Because in some sense it has learned the distribution over sentences, words, and all these things, right? So it's a much more complex distribution than say Bernoulli or Gaussian, right? Which have like only 1 or 2 parameters, but your generative models like ChatGPT will have billions of parameters. Okay, so this is actually a very nice topic, generative models and generative modeling. Maybe we should discuss it.
We do generate also, right? For some other purpose, right? We do generate data after modeling or getting an idea about the real data. We just generate our own data and do some needed.
Yeah, so that is one use case of generative models. The other use case is for classification, which you will see in week 8. Okay, so once you learn once you learn a generative model of the data, you can then use Bayes' theorem to compute which class a particular point will belong to. Okay, so this class of models is one class of models is called naive Bayes, right? It's called the naive Bayes model, which we will study in week 8, and it's based on this whole generative process. So this MLE, you must, even if you forget this GMM and EM algorithm, it's okay. But for as far as this course is concerned, please don't forget MLE and Bayesian modeling, because MLE will come in week 5. It will come in other weeks also. Bayesian modeling will come in week 6. Okay, when you're trying to understand linear regression, there also Bayesian modeling will come. So these are two important topics that are going to keep coming. So,
sir.
Yeah.
Hello. So just a related point to this, we are talking about MLE, right?
Yes.
So is there any specific reason we are talking about MLE? Because in stats 2, if I remember, we had studied, two methods of estimation. One was, I think, methods of in this MLE, and the other one was, and the other one was method of moments.
Yeah,
right. Method of moments, right? And MLE. So any specific reason why we are giving importance to MLE only, not other methods?
Good question. I don't have the answer. I don't know why. MLE is.
We are giving importance to two methods, right? MLE and Bayesian.
But Bayesian is derived from MLE, no? Only like we are taking help of MLE only, maximum likelihood estimation.
No, right? They are different.
No, I got your point. I got your point. That's what you're saying. We can deal with MLE separately also, and we can deal with Bayesian separately also. But anyhow, MLE is becoming a part of Bayesian also. So somewhere MLE is coming again and again, and we are not talking so much about method of movements. No problems. That's fine.
Okay, so this method.
There is no MLE in Bayesian. That's what I'm trying to say.
Not MLE likelihood. Okay, yeah, okay. See,
there you differentiate. You identify this thing. In Bayesian, there is no differentiation. Nothing.
No, there is one component called likelihood, no, in Bayesian also. If you see.
But but likelihood is basically it's a generic word. That's what I think. But MLE and maximum likelihood estimation method and Bayesian are two very different things. There's no connection between the two, if I'm not wrong.
Okay.
Is that correct, Srikanth sir? I mean, I've made a wrong statement.
No, MLE, they are different. But I think maybe what is meant is the likelihood is a part of both.
Yes,
correct. That's correct. That's correct.
Because we are maximizing likelihood over there itself. No? In MLE also we are maximizing likelihood.
Right. So, which is preferred? I don't know. So, for example, if you look at the references for this course, right? If you look at Bishop's PRML is one of the references.
That's what I'm saying. That's what I'm saying. So, sorry.
Which one? What did you say, sir? What did you say, sir? Bishop? What did you say?
So this Bishop, right? So Bishop, if you look at the text.
Yeah, that book, right?
Yeah. So they have a heavy Bayesian leading. So if you look at any chapter, they say, okay, Bayesian methods are like this, or the Bayesian methods have approached the problem like this. So I think there is a slant towards that in that book. But in general, if you ask why, so your question initially was why is MLE so popular? Is that the question?
Yes, sir, that was my question. Why we are not talking about method of moments?
Okay, I don't know why MLE is better than the method of moments. I'm not sure.
No, GP, I wanted to clarify. We are not in the Bayesian method. We are not maximizing anything.
No. We are. See, we end up maximizing if you want a point estimate, right? So if you want a point estimate, we also maximize in the case of MAP. If you want a maximum a posteriori estimate, you have to maximize.
That you're not maximizing. That's an expected value.
No. Expected value is one of the ways of getting a point estimate, right? So there
is correct. There is mean, there is mode. You can probably create your own also. All I'm saying is that in Bayesian, the idea is you have a distribution, then you have a data which is observed. You combine the two and you get a new distribution, right? That's why they call priors, right? Conjugate priors or whatever. There is no maximization there. We are just, once the data is kind of taken into the picture, the distribution is updated in some manner. The concept of maximization doesn't come there, is what I'm trying to say.
Right. Yeah, it is not there inherently, but you can, if you want a point estimate through the mode, then you have to maximize. Only
we are not no, we are not maximizing. That's what I'm saying. Sorry, I'm just belaboring this point. It's just you have a certain distribution posterior. The mode or map or mean, whatever it is, it's just a function of that distribution. There is no maximization.
No, you're missing the point. See, I agree. The posterior, getting the posterior distribution is the idea of Bayesian modeling. But
correct.
The point, if you want a point estimate, there are many methods. The mean is one of the methods. There you don't need to maximize. It so happens that if you go for the mode, then you have to find the maximum of the posterior. Okay, so there is a
but that is not maximization. Maximization, we are not changing theta after that. We are not changing the theta.
We are right. We are looking for the maximum. We are looking for that theta which will give you the maximum of the mode. See, in that sense, MAP and MLE are very much. MLE is solving one optimization problem. MAP is solving a different optimization problem.
No, I know why you're saying that, but I don't agree with that. Okay, we'll discuss this later.
No, what? Tell me. No, it's okay. You tell me which part is not. You don't
okay,
agree.
let's say posterior is beta distribution alpha beta. Let's say okay.
Okay.
Let's say posterior. Now, what is the mean? Mean is alpha by alpha plus beta. Correct. Now, what is mode?
You tell me. What is the mode?
Alpha minus 1 by alpha plus beta minus 2.
How did you get that?
That is because that's the nature. That's the it's like, you know, there'll be some derivation behind it.
What is the derivation?
It's a closed form derivation. I don't know.
No, that's what he equated it to 0 and then got that.
That is the point I'm making, right? That's the point I'm making.
He took the derivation, he equated to 0 and then he got it.
Yeah,
Alpha
so
minus 1 by alpha plus beta minus 2.
Right. So the mode is the. So you have to go and read up what is MAP, right? MAP is what it is trying to solve an optimization problem. It's trying to solve a maximization problem on top of the posterior, right? You don't get the mode just because it is closed form doesn't mean that there is no backdrop to it, right?
Okay, I'm going to read. I'm going to read up about that and come back.
Yeah, so I agree that in Bayesian modeling you don't have to do all these things. I mean, certainly, right? Of course, you're right.
Because what I was trying to say is, once the distribution posterior is decided, the alpha beta doesn't change.
Correct. Alpha beta
doesn't change. Whereas maximization MLE, you are looking for the alpha beta.
No, right? In MLE, where are you looking for alpha beta?
I am looking for parameter. Yes,
the alpha beta are hyperparameters, right? So
okay, or whatever. Whatever is the distribution, equivalent distribution, right? Whatever you end up with okay, they're not like to like comparable that way. But what I'm trying to say is here, once alpha beta is it's fixed or whatever distribution you end up with. Let's say you end up with a Poisson distribution, right, as a posterior distribution, right? Then the parameter doesn't change. There you are looking for the right parameter. That's all I'm trying to say. That's why the maximization thing makes sense there.
Here also, see, okay, what is the output of Bayesian modeling?
I'm just updating. Output is some distribution.
It is some distribution, right? So that it stops there. Now, if you want a point estimate from Bayesian modeling, there are two ways to go about it, right? At least that's what we have done in the course. One is the mean of the posterior, right? One is the mean of the posterior.
Correct.
Okay. The other one is the mode of the posterior.
Correct.
Right. It so happens that the mode of the posterior is nothing but maximum value at which the distribution or the argmax at which the distribution achieves its maximum value. So this is very similar to MLE, right? You're solving a maximization problem.
Maximum is not maximization, is what I'm saying. Probably we are saying the same thing. I have a different way of articulating it. Probably I'll read about this and I'll post it back, or we'll catch up on the next session.
Yeah, sure.
So I probably am saying the same thing, but I'm not able to find the right words.
Right. Okay.
Sorry.
Can I ask a question?
Yeah, go ahead. Yeah.
So in MLE, we're getting a one single estimate for the parameter.
Correct.
And in this Bayesian estimate, we're getting a whole distribution of the parameter, right?
Correct. We are getting a whole distribution of the parameter.
So MLE gives you a sort of like a point estimate. And in Bayesian, you will have to get the point estimate through the mean and the mode.
Exactly. Yeah. So in Bayesian, if you want a point estimate, then you'll have to resort to either mean or mode.
Because you are ultimately getting a distribution of the parameter.
Correct. Correct. Exactly.
Yeah. Okay. Thank you.
Yeah, Karthik, I have one doubt from the lectures. In one of the initial MLE lecture, he said that the Gaussian model, we cannot use it to predict the discrete values because it is continuous, so the mean will become 0.
Mean will become 0.
One point he said we can't use like to predict the height to model.
Oh,
he said the probability from the lecture slide, but immediately he used the same Gaussian model. Instead of P, he has put function of. That point I'm unable to understand that.
Right. So what you would have mentioned
I remember that.
But we use the same thing, same formula. That
No,
P
he said we shouldn't use P, we should use F because F indicates PDF and P indicates probability, which is PMF.
Okay.
It's just a notation thing.
Okay. Yeah. Thank you.
I think this is related to that in case of continuous distribution, the probability of at a particular value will always be 0.
Correct.
So we cannot have that.
A continuous function.
So we in case of continuous, we have a range. We don't get a the probability of particular value.
Okay, because he changed to F, I'm getting confused. Okay, but anyway, both are distributions, right?
Yeah.
Okay, thank you.
If before concluding, could we possibly find the mean and the mode of the last question that we have done? Example 3.
Okay. Example 3 was.
So I'm getting with the mode being more than 1. That's not possible, is it?
I made a mistake in the slide, right? What value of alpha and beta are you using?
I think we were supposed to get
8.1 and 1.1. Is that what you're using finally?
Okay. Yeah, all right, fine. It's getting close to. Fine, I got it. Thank you.
No, sir has written 9.9, so there is a correction. It should be 8.1 and 1.1. That alpha beta I have to take.
There's a mistake. All right, thank you.
Right. Okay, I think.
Sir.
So, yeah.
If no one is having any question, then I have a couple of questions. And we should not, and you can switch off recording also because the duration of the video should not get extended. I have only a few doubts, sir. So
okay.
I will not take more than 5 minutes, but the duration of the video should not get extended, so you can switch off recording.
Yeah.
Sir, during during the session, today's session, sir, you made a very valid point that couple of topics it may happen that